All right, so we'll go through Maxwell relations. All right, so these are what we call Maxwell equations. So these they are just there to relate how the variables would be actually affecting the thermodynamic equations of which we have them here. All right. So even get a trick on how to name these. I mean, how to come up with these Maxwell equations because it's not easy to master all of them. There are four in total. All right. So without even wasting our time, shall we start? So this covers industrial chemistry, pure chemistry, and other chemistry, all right? But basically Maxwell relations, all right? For CBU guys, you are lucky. So what you are going to do here is I'll even give you a trick on how to name this. So shall we start? All right. So Maxwell relations, they are of this type, by the way. So what we need to know is that first thing that I'm going to do, I'll do this. I'll say a supervatra, all right? So I'll say supervatra represented by SPVT. This is my supervatra. Then here I'll say, how good are you? All right? So I'll say, how good are you? All right. So from there, then what I'm going to do here, I'll write a box. All right. So I'll write a box as follow. So just master what I want to do here. All right. So have you seen this box that I've written here? So what I'm going to do here, I'll say SP then VT on top. So I'll start with S. All right. P. Then the vector I was talking about down here. All right. So after doing this, I'll say from S here, I'll drop a line like this. All right. Have you seen the way it is dropping again? I'm dropping from P. The line should be straight, by the way. Then I've done with SPVT, which is super vatra. Then what I'm going to do here is I'll say, how good are you? So I'll start the same how here. All right. Then good here. Then are you, which is A, then the same U here. All right. So have you seen the way it is moving? So now how do we come up with these Maxwell relations or equations that we saw on the previous page? All right. So what I'm going to do here, I'll say the first equation that I'm going to extract is for entropy. All right. So what I'm going to do here is I'll say this H, I'll start with this H, by the way. Look at me. Pay attention. So this H I have here, I'll say DH. All right. So these are the subject DH, DG, DA, DU. All right. So this can also be DE because that is internal energy. Anyway, away from that, we are saying DH. All right. So DH is equal to what? So what I'm going to do here is I'm at H, right? So H is in between S and P. All right. So I'll say DS. All right. Again, a space there. Then I'll write DP. Have you seen what I've done here? I'm writing this and this, all right, as my change, which is the DSDP. So you write what is on the middle there as your subject. Then you come and get this and this as your differential equations. These are the changing point. So these are the point you can see. So it's at the end. So it was changing there. It changed. Let's say we had 20 here. Here it will be something else. So that's why we are writing DP, DS. We are at the end. Okay. So from there, what you're going to do is, have you seen S here? So the one I want to find now coefficient. So this S is pointing to T, right? So S is pointing to T positively. So I'll say it's following the arrow nicely. So that will be my TDS. Then the same P again is following nicely the what? The V. So I'll say V. So it's not negative. So I'll write plus there. Okay. Hope that is clear. So this is one Maxwell equation. All right. So the second equation that we can have here is I'll write DG if I want. Okay, DG. So This dg now is equal to, have you seen g here? All right, so I'll write dp dt. All right, so I'll say dp, all right, then dt, because it's in between this, so I'll say dt, like that. Okay, so after writing this, I'll say now it is in between this and this. Have you seen? So this t here, where there is t here, or let me start with p. P is pointing to V, right? Is positively pointing the arrow because the arrow is like this. So this will be just V. All right. Then here, since we are dealing with P and T, so the T now is now against the arrow. So this will be negative. All right. This will be negative. S is giving negative S because it's now against the arrow. So that will be negative S, like that. Hope that is clear. Then the other equation that we can draw from here is dA. All right. So we can see A is between these two guys. So what we are going to do is we'll say dV dt. All right. So I'll say dV, then dt. So what are the coefficient and their charges? So if I get this t where there's t, what is pointing there is negative S. So I'll say negative S. All right. Then here it's V. So V is what? Giving positive P, right? No, again, we are against the arrow. So we are going like that, which is against. So this will be negative P. All right. Hope that is clear. Then the last one that we can have for internal energy is, so we are saying du, all right? Du is in between of what? It's in between S and V. So I'll say ds if I want, then dv. All right. So what is in between? For ds, s is pointing to t, so that will be just positive t. All right. Then this v dv is pointing to negative. It's against the arrow to p. All right. So say negative p, like that. So these are the four Maxwell relations or equations. So this is how you'll be coming up with them. Then now drive some relation, one or two relations, then will be done from there so that we can start that. So you can get this one and come up with a relationship, and also this one you can get and come up with a relationship. Even this one you can get and come up with a relationship. Even this one you can get and come up with a relation. So we'll demonstrate one or two. So let's go. I'll pick N. All right. So if I want, I can pick the last one. Let me pick the last one. Then I'll drive the relationship. Then we should know how to drive the relationship from there. Okay, so let's go. So suppose now we have this third one of which I said, which was giving du, right? Giving us t, all right, ds, then minus p dv. Okay, so how do we do this one? So what we do here is you get first this one. You say at constant, you want to just to cancel one thing here. All right, so I can say at constant, you concentrate on this d something, dv ds, d something, d what, dp dh. Okay, so what you do is you say d. So before even that, I'll say at a constant. Okay, at constant, I just say at constant s. All right. So if at constant s, the meaning ds is 0, right? So we'll say du is equal to negative p dv. You've seen, we want to cancel this v, so we'll differentiate with respect to v. All right. So I'll say differentiate this one with respect to v, so that will be du, all right, dv. So that is done at a constant, the other, which is s. All right. So I'll say dv. So we said this is done at a constant entropy. So then this is equal to negative p dv over the same dv. So this v goes. So we'll have du over dv, then at a constant entropy like that is giving what? Negative P. So from here, what we are going to do here is, this is now our one of the equations. So I'll differentiate this one, all right? I'll, I'll differentiate this one now. I'm differentiating with respect to what? To S, the other one again, okay? So what you do, you have used to differentiate what? V. So this time around is now the S you are differentiating. That is the one you're giving respect. Remember, S was at constant. Now we are putting V at constant. So what I'm going to, the same thing here, I'll say the, let me write it here. We have it here as, so you can write as equation 1 there. So we have it as du over dv, all right? Then at constant entropy, like that, is giving negative pressure. So what we do from here is we'll say we are differentiating this one with respect now to what? To the other one, which is S, all right? This is, you can forget if you want. So I'll say differentiating this one with respect to S. All right, against this du which we have, but let me write like this. Let me write like partial derivative of internal energy over partial derivative of the same V. Okay, forget about this S if you want. So it was at constant what? Constant this one. So now it's at constant volume. All right. So it's at constant volume now. What is changing now is the entropy. So say negative, all right, partial derivative of P over the same thing you have done here, which is partial derivative of S. Okay. So have you seen what you have done here? So say this one is now d squared, partial derivative squared over, all right, we have partial derivative of S, then partial derivative of V, giving us what? Negative partial derivative of P over partial derivative of S. So remember, this is done at constant volume. Okay, so this is one thing we need to know, all right? So I'll bring this one here, all right? So I'll say partial derivative squared U, all right? Because when you multiply this and this is giving in partial like that. So then you multiply, I'm just bringing this one here, all right? So I'll say partial derivative of S, partial derivative of V, then is equal to negative partial derivative of P, then partial derivative of S at constant. By the way I'm writing partial. Okay, so this is the equation 1, all right? So away from this now, forget about this. I'm sure I've written these steps somewhere or you have understood. I'll take it like that. Okay. So from there, then what you are going to do here is I'll get the same relationship. Then again, I'll drive something like this from the same equation, guys. So you get from the same equation. So the same equation here that you can see here, all right, du, all right, is equal to T ds minus P dv. All right. So what I'm going to do here is I will say at constant volume now. If at constant volume, then in here it will be 0, right? So it will be just du, all right, is equal to T ds. Have you seen the game? It's very simple, guys. So what you do here is after doing this, you say now, differentiating this one with respect to entropy because you want to cancel this one. So you say, you differentiate this one with respect to entropy. So this will be d what? ds then is equal to T, all right, ds again ds, like that. You see? So these will go, right? So say du over ds is equal to T. Okay. So it's equal to T. So what we have here, we have to do is now again to differentiate twice. Okay, so is equals to T, like that. So now I'm differentiating this one again with respect to the other one. Remember here, it was at constant volume, right? Constant volume. Now is at constant. I'm differentiating this one now at constant entropy, but differentiating the same volume which is here, all right? Because I've already have what? ds. So I also need to have dA dV. So I'll say um partial derivative of this function, then with respect to v, all right? So that is partial of internal energy, then partial derivative of entropy, all right? Forget about this v, then here it will be now partial derivative of t over partial derivative. We said at what? You are giving respect to what? To v. So this is partial derivative of v, like that. So here it's now at in our constant entropy. You get? So if you notice here, this and this is just the same. So this I can be just written. It can be written as this is partial times partial. That is partial squared. By the way I'm writing partial is something else. Okay, so this will be partial squared. All right. Then we have then over we have partial derivative of v, then partial derivative of s. Okay, which is giving us positive partial derivative of t, then partial derivative of v at constant entropy. All right. So since we have at constant, you can see this thing here is equal to this here. All right. So meaning that this guy is equal to that. So therefore, all right, I'll say this thing which is here negative partial derivative of pressure, then partial derivative of entropy, all right, at constant volume is equal to partial derivative of t over partial derivative of v at constant entropy. So this is one relation, okay, for Maxwell relation. So that's how you can do it. We can even try another one if you are not satisfied. So let's try another one. So this is one relation. So you can be asked to show that this is equal to this. So you need to note, say this one involved which type of Maxwell relationship. So that's how you can differentiate. Sometimes you can be given derive the relationship from this equation. So let's go. So again, I can give another one which was for internal energy. No, let me give another one. All right. So let me give for free energy. So free energy is given as dA is equal to negative P dV. All right. Well, we have seen how we can drive this. This one carries all the negative because it's down. How good are you? Then we have T there. So what we are going to do here is I will say at constant what? I can start whatever I want. So I can say at constant temperature if I want. All right. So if I'm saying at constant temperature, then this will be dA. dA is equal to negative P dV. Because at constant, this one is now 0. All right. So what I'm going to do here again is you can be writing, say, equation 1, equation 2 if you want to get those marks you want. So then what I'm going to do here is I'll differentiate this one with respect to what? To volume. So this will be dA dV at constant one. Remember, we're still having constant temperature. So this will be equal to what? Negative P dV again dV. Throughout, this will be 1. So this will now be dV, all right, at constant that is equals to negative P. So we differentiate this one now, this one with respect to the other one, okay? So remember here is at constant temperature. So now we'll differentiate at constant what? Constant the other one which was V. All right. So what I'm going to do here, I'll say this one, the differential with respect to volume, right? Open bracket, we have the partial derivative of free energy, then partial derivative of volume. Is this making sense? No, we have volume there, right? Let me do this. We can't have the same thing here. So this is at constant pressure. So we are differentiating now at constant volume. All right. So now meaning that we are differentiating at constant. We are differentiating with respect to t. All right. Very okay. So what you are going to do here is we'll differentiate now with respect to entropy. So remember it was at constant temperature. So now it's at constant T. So we want this the same temperature to change. Okay. So we'll say partial derivative of, then we'll have partial derivative of T there. All right. So now we are holding this one. So say partial derivative of free energy, partial derivative of volume. Okay. This is at now constant. Um, is at constant what? It was at constant temperature. Anyway, don't mind this. Then we have partial derivative of pressure over partial derivative of the same temperature. Okay, so you have seen this. So what you are going to do here is this is equal to, or I can simplify this as this is partial times partial, that is just partial squared. Okay, then we have free energy there over, we have partial derivative of t, then partial derivative of v. Then it's giving us what? Negative partial derivative of p over partial derivative of t. So this is one. So this is done. This was done at constant temperature. This is done at constant volume. All right. So this is one equation we need to understand. So let me light something here, then we'll be able to actually. So in short, this is the one relationship we have been looking for. So forget about this one. I'll bring this one here. So I'll say, I'll just light it properly. Okay. So I'll say this is partial squared, then change in internal free energy, then partial derivative of t, then partial derivative of v is equals to this. So forget about this. So this is done at constant volume. Hope I'm not confusing someone there. All right. So there are a lot. So we'll just try to show this one, then we'll be done. So for this one again, now it was at constant temperature. Remember, now I'll do it at constant volume. I'll start with constant volume. So we have the equation as dA, which is the free energy, is equals to P dV, all right, minus S dt, all right. So what we do here is now at constant volume, all right. So at constant volume, meaning this will be 0. So we'll have dA, all right, is equal to negative S dt. Okay, so differentiating, we want just to cancel this dt. So I'll differentiate throughout by what? By dt, all right. So this will go. So we'll have dA over dt is equal to negative S. Okay, so again, I'll differentiate this one. Now this was done at constant volume, remember. So I'll differentiate it now at constant temperature. So I'm differentiating volume now, which is there. So I'll say change in of this function, then with respect to change in volume, it will be dA, or let me just use partial here. All right, partial derivative. So that would be now partial derivative of A over partial derivative of T. Okay, so then this will be partial derivative of, so this is negative, partial derivative of S, then partial derivative of V. This and this, you can see they can multiply partial and partial. That will be partial squared A, then over, we have partial V, again partial T, which is equal to what? Negative partial S, over partial V, this is done at constant. Remember, this was done at constant volume. This was done at constant volume. This is now done at constant temperature. All right. So you can see this here and this, they are equal. So meaning that this thing and this thing we have here is, so we have negative here, we have negative partial derivative of P over partial derivative of T. All right. Then constant volume is equal to this thing that we have here. So this is partial derivative of S partial derivative of V. This is done at constant temperature. So this is another relationship we can obtain. You can see. So you can be writing equation 1, equation 2, something like that if you want those marks you want. Then, but this is what is there. You differentiate the first one, you keep the other one constant. Then you continue differentiate this one twice. Okay? I mean, you differentiate this equation, you keep the other variable constant, then it will cancel. You remain with one. That one you have remained, differentiate and remain with that later. Then again, differentiate the other one, the one you had kept zero, I mean constant. Then you see what will happen in it. Then you come again, you do the same again. You start, you just change the way you start. Then you find that you find the relationship. So otherwise, this is what is all about Maxwell equations. They're a lot. Just try to practice those two. You'll be able to come up with the same thing. So thank you very much for watching the video. Make sure that you master this box, all right? Super Vatra, okay? Super Vatra, how good are you, all right? So Super Vatra, how good are you? Then these are the subject we have there. All right. Thank you very much for watching the video. Please subscribe.